Welcome back to The Effect. We are still talking about regression discontinuity. So in the last video, I showed you some basic ways to estimate a regression discontinuity estimate. And that involved running a regression on one side of the cutoff and another regression on the other side of the cutoff, and then seeing where the two lines met up and seeing what kind of jump we kind of expected at the cutoff point. However, there are a lot of other considerations that we have to deal with. I mentioned, we have to think about, well, what is our bandwidth, right? How far outside of the cutoff are we willing to consider in our analysis, right? If you include a bunch of data that's really, really far from the cutoff, well, that sort of defeats the purpose of the regression discontinuity in the first place, which is to say that we think that people just around the cutoff are basically comparable, except that some got the treatment and others did not. However, if we limit the sample to just around the cutoff, then we lose a lot of observations, and then we are going to have some problems with our statistical precision. We also talked about using polynomials to deal with nonlinear relationship between the running variable and the outcome, right? If the data is curvy, then your line should be curvy too. Now, both of these issues are very difficult and they're important to deal with when you're doing regression discontinuity because you need to get your estimate at the cutoff as correct as possible. So there are a couple things that people do in order to, first of all, try to sort of balance the difference between the precision of having more observations far from the cutoff and the bias reduction that you get from being close to the cutoff, and also to deal with the fact that we want to maybe allow for a little bit of a curvy line and allow for some flexibility in our regression line. So the first thing I want to talk about is the use of weights. So I mentioned using a regression where we fit a line on either side of the data. However, you don't necessarily have to allow each point in your data to count the same in your estimation. You can use weights that will allow some observations to have more influence on your estimation of the regression line and some values to have less influence. And in particular, the way that you might structure this is to have the points that are closest to the cutoff count the most. So you might say something like, okay, if you're right next to the cutoff, then I think that you are really, really unbiased. I can compare you right on the other side of the cutoff, no problem. And as I move further away, I'm like a little bit less certain about these people, a little bit less certain about these people, a little bit less certain about these people, and I don't think these people are comparable at all. You can use weights to get that exact same idea into your actual analysis. You can say something like, okay, here is my kernel function. A kernel function is a function that is centered around 0 and is typically at its tallest at 0, and then descends as you get further away from 0 until finally you reach an actual weight of 0. And if you are right in the center, if you are right at the cutoff, then you get the biggest weight. And as you move further away from the cutoff, your weight declines until you finally get far enough away that I say you don't count at all. And now there are a number of different ways that you can implement a weight in your regression discontinuity analysis. There is, for example, the triangular kernel, which looks exactly like this. It looks like a triangle. There's the Epineshkinov kernel, which is a bit more curved. But the basic idea with all of them is that the closer you are to the cutoff, the bigger of a weight you get. And then as you move away, you reduce your weight until finally you get to 0. This allows you to include a few more observations in your analysis while reducing the impact that they're going to have on your bias, right? If here's your triangular kernel, then you say, if I just limited the data to just right around the cutoff right here, that's not a lot of observations. And if I allow everybody in, well, that's maybe some observations that I think might maybe introduce some bias. I think they're maybe okay, but they might not be. But what we can just do is say, hey, these people are okay, but only at a very reduced weight, and I will put most of the weight on the people I'm really, really certain about. That is what a triangular kernel can do for you. Similarly, with an Epineshkinov kernel or any other sort of kernel that weights the observations really, really near the cutoff as highly as possible, and then it declines as you move farther and farther away until eventually you get to the edge of your bandwidth and they become weights of 0. This allows you to, like I mentioned, split that difference between the additional precision of allowing more observations and also the increased bias of allowing more observations. So you sort of get the best of both worlds at least a little bit. So that's how we can deal with weighting our observations more heavily the closer they are to the cutoff. How about the whole thing with the curviness of the line? That you might want a straight line, you might want a curvy line. What exactly are you going to do? So we talked last time about adding polynomial terms to your analysis. Instead of fitting a straight line on either side of the cutoff, you can fit a curvy line on either side of the cutoff and see what the jump is like there. And that can solve some problems for us. However, we might also consider doing something called local regression. What local regression does is it does not fit a single line over here and a single line over here. Instead, it moves along the running variable, taking a little window of data at a time. And every time it takes a little window of data, it fits a different regression, sometimes a linear regression, sometimes a polynomial regression, but a regression nonetheless. And then it produces a set of predictions just for the data in that narrow little range. And so in doing so, you allow the model to be curvy, because you can say, okay, over here the slope looks very flat, so I'm going to put a very flat line right there. And then move a little bit over. Okay, now it looks a little bit steeper, so I'm going to put a little steeper line there. And then a little steeper than that. And you move along and you allow the slope to be changing continuously, and you get something that looks like this. Now, this does a couple of things for us. So first of all, you'll notice I'm looking at a little window one at a time, which already sort of incorporates our bandwidth idea. Imagine what's happening right next to the cutoff. Well, right next to the cutoff, if this is my cutoff line, and this is the window that I'm looking at for my local linear regression, I'm only using observations in this little window to estimate my regression at that exact particular point. And because of that, I'm automatically including a bandwidth in my analysis. To some degree or another. I have either a bandwidth or a weight, depending on exactly how you put together your local linear regression. So this allows full curviness of your regression line. It can go in any shape that you like. It does not have to be a straight line. This has some attractive properties because it makes a lot of sense with what we're trying to do with regression discontinuity. It is a little bit less precise than just fitting a regression, right? We're allowing something to be more flexible. In statistics, that almost always gives you less precision, but that's the trade-off that we have. The other thing to point out is that by focusing on a little window just one at a time, it allows us to use a more linear approach. We don't necessarily have to have a whole bunch of polynomials to fit a very curvy line. In fact, you probably don't want a whole bunch of polynomials to fit your very curvy line, especially if you're using bandwidths, because if you zoom in very closely, pretty much everything looks linear. You could have the whole wildest kind of curve that you could possibly imagine, but if you look just at a little tiny window, it's straight. In this little tiny window. You zoom in far enough on anything, it looks like a straight line. That's why when you look at the horizon, which is a very zoomed in picture of the round Earth, you get what looks like almost a straight line, because you've simply zoomed in far enough on a tiny little portion of the Earth. So those are two different things that we can do to incorporate some of the issues we talked about last time with estimating regression discontinuity effects. To sort of split the difference between the increased bias from having more observations, but the reduced precision of having fewer, we can weight things to allow a little bit more observations without allowing them to take over and introduce too much bias to our analysis. So it's a bit more of a nuanced way of allowing for our bandwidth to work. We can also, instead of having a straight line or even a polynomial line, allow for local linear regression, or local polynomial regression, just local regression in some way, where we're allowing the slope to change depending on which range of data you are looking at. Which means that once we get right up to the point, we are largely looking at data just around the cutoff, which is largely what we wanted to do anyway. This approach does reduce our precision, which is a problem because we're already in a low precision zone when we're working with regression discontinuity, but it does solve some problems for us in regards to functional form. All right, that is it for this video. In the next video, we'll be talking about some ways that we can check the plausibility of the assumptions we need to make for regression discontinuity to work. Thank you.